You are dragging a stone block across dry sand, roughly 4,500 years ago in what is now Egypt. The block weighs about 2.5 tons. You and 11 other men are pulling it with ropes woven from papyrus fiber, and every step is a negotiation with the ground. The sand piles up in front of the block. The ropes cut into your shoulders. The friction between stone and earth is so enormous that for every unit of force you put into moving forward, more than half of it is consumed by the ground just saying no. You are losing a fight with physics, and you do not even know the word for physics, and then someone walks to the front of the sledge with a jar of water and pours it onto the sand. That scene is not hypothetical. It is painted on the wall of a tomb in Deir el-Bersha, Egypt, dating to roughly 1880 BC. The tomb belongs to a nomarch named Jehudi-Hotep, and the painting shows 172 men dragging a colossal alabaster statue on a wooden sledge. At the front of the sledge, a single figure stands pouring liquid onto the sand in front of the runners. For decades, Egyptologists assumed this was a ritual gesture, a purification ceremony, some kind of religious act that had nothing to do with moving the statue. Then, in 2014, physicists at the University of Amsterdam ran the experiment. They built a small sledge, loaded it with weight, and dragged it across sand in a laboratory. Dry sand piled up in front of the sledge, dramatically increasing the force required. But when they added water, a specific amount, roughly 2 to 5% by volume, the sand stiffened. Tiny capillary bridges formed between the grains, binding them together, preventing them from bunching up. The pulling force dropped by half. The Egyptians were not performing a ritual. They were performing tribology, the science of friction, wear, and lubrication, 4,000 years before anyone gave it a name. And that is where the story of bearings begins. Not with a ball, not with a race, not with a steel cage, with a jar of water poured onto sand by someone who understood, at a level so intuitive it looked like instinct, that the enemy of all motion is the surface it moves against. The entire history of the bearing is the history of humanity's war against friction. And it took us 5,000 years, a dozen civilizations, and at least 4 independent engineering traditions to fight that war to anything resembling a victory. So how did humans invent the bearing? Let's start with what friction actually is, because most people have a gut sense of it but have never thought about why it exists at all. When two surfaces press against each other, they look smooth to the naked eye. They are not. At a microscopic level, every surface is a landscape of peaks and valleys, tiny irregular bumps called asperities. When you press two surfaces together and try to slide one across the other, those asperities interlock. They resist, they deform, they break, generating heat. That resistance is friction. And it is governed by laws that were first formally described by Guillaume Amontons in 1699 and later refined by Charles Augustin de Coulomb in 1785. Friction is proportional to the force pressing the surfaces together, and it is largely independent of the apparent contact area. A large block and a small block of the same weight dragged across the same surface experience roughly the same friction. That feels counterintuitive. But at the microscopic level, both blocks are making contact at roughly the same number of tiny asperity points. The weight determines how hard those points press together. The area is irrelevant. But here's the part that matters for bearings. Rolling friction is dramatically lower than sliding friction. Dramatically. The coefficient of sliding friction for, say, steel on steel is roughly 0.6 to 0.8. The coefficient of rolling friction for a steel ball on a steel surface is roughly 0.001 to 0.03. That is not a small improvement. That is a reduction of roughly 99%. Rolling does not eliminate friction. It replaces the destructive surface shearing mechanism of sliding with the gentler, deformation-based mechanism of rolling, where the primary resistance comes from the tiny elastic compression of the surfaces at the contact point. The material bends, springs back, and the energy loss is minimal. Every bearing ever invented exploits this single physical fact: roll, do not slide. And humans figured that out long before they understood why it worked. The earliest known exploitation of rolling to reduce friction is almost comically simple. Logs, tree trunks placed under heavy objects so that instead of dragging them, you roll them. We do not know exactly when this technique was first used because wood does not survive thousands of years in the archaeological record the way stone does. But we know it was ancient. Depictions of Assyrian laborers using log rollers to transport massive stone sculptures date to the 7th century BC. The technique almost certainly goes back much further, possibly to the construction of the great megalithic monuments. Though the exact method used to build the pyramids at Giza remains one of the most debated questions in archaeology. But here's the thing about log rollers. They work. They reduce friction enormously, but they are not bearings. A bearing, in the engineering sense, is a device that constrains relative motion between two parts while reducing friction between them. A log under a stone block just provides a rolling surface. The block rolls off the logs, you have to keep picking them up from behind and placing them in front again. There is no constraint, no containment, no design. It is a principle without a mechanism. And the step from principle to mechanism took thousands of years. Think about what that gap means for the story of bearings. Humans understood the advantage of rolling motion for millennia before anyone figured out how to package it into a device. The bearing is not just the discovery of rolling. It is the engineering of rolling, the containment of it, the control. And that distinction is what separates a log under a rock from the machine inside your car's wheel hub. The first real mechanical application of rotational bearing surfaces appeared not on a road but on a table, the potter's wheel. Around 3500 BC in Mesopotamia, modern-day Iraq potters began using rotating platforms called turnettes to shape clay vessels. The earliest versions were slow, hand-turned discs mounted on a simple pivot, a vertical peg seated in a stone socket. That pivot point is, in the most fundamental sense, a bearing, a fixed point around which rotation occurs. The socket stone reduces wobble. The peg provides a stable axis. The whole system exists to allow one surface to spin against another with as little resistance as possible. Archaeological excavations across the Near East and Egypt have recovered these socket stones, smooth-worn from decades of use. They are crude, they are primitive, but they are bearings, and they predate the wheel on a cart by roughly 300 years. That chronology is worth pausing on. The wheel for transportation, the thing most people picture when they think of the wheel, appeared around 3200 BC. The oldest surviving physical wheel was found in 2002 in the Ljubljana marshes of Slovenia, radiocarbon dated to approximately 3150 to 3350 BC, made of ash and oak, with a square central hole indicating the wheel and axle rotated as a single unit. But the potter's wheel came first. Rotation as a craft tool preceded rotation as a transportation device. The idea of spinning something on an axis for work came before the idea of spinning something on an axis to move, and both of them required a bearing, even if nobody called it that. Now, the wheel and axle system used in the earliest carts and wagons was a plain bearing, the simplest kind. A cylindrical surface rotating inside a cylindrical hole. The axle turns inside the hub, or the hub turns around the axle. Wood on wood, sometimes lubricated with animal fat or vegetable oil to reduce friction and heat. This is the technology that moved every cart, every chariot, every wagon for roughly 4,000 years. And it works, but it has limits. Wood wears, fat dries up, the surfaces grind against each other and generate heat. Over long distances, at high loads, plain bearings fail. The hub seizes on the axle. The axle snaps, the wheel falls off. For thousands of years, the limiting factor on how far, how fast, and how heavy you could transport anything was the friction between a round stick and a round hole. And then the Romans did something extraordinary. In the volcanic hills south of Rome, there is a small, deep lake called Lake Nemi. It sits inside the caldera of an extinct volcano, surrounded by forest. In antiquity, it was sacred to the goddess Diana. And in the 1st century AD, Emperor Caligula built 2 enormous ships on this lake. Not warships, pleasure barges. Floating palaces, roughly 70 meters long, fitted with marble floors, heated baths, and rotating platforms for statues or machinery. People had known about these ships for centuries. Fishermen snagged their nets on the hulls. Renaissance treasure hunters dove down and pulled up bronze fittings. But it was not until 1929 that Benito Mussolini ordered the lake drained to recover the vessel's hull. Between 1929 and 1932, engineers pumped out enough water to lower the lake level by over 20 meters, exposing both ships on the lake bed. And what they found inside changed the history of engineering. On the decks of the Nemi ships, archaeologists discovered rotating platforms mounted on what can only be described as ball bearings. Bronze balls, carefully shaped, sitting inside a wooden race, supporting a turntable that could rotate freely under load. One platform used ball bearings. A second used cylindrical roller bearings, and a third showed evidence of tapered bearings, 3 different types of rolling element bearing on 2 ships in a lake in Italy 2,000 years ago. The Romans had not just discovered the principle of the bearing, they had engineered multiple variants of it, ball bearings for one application, rollers for another. tapered elements for a third, each one optimized for a different kind of load. Think about what that means. Before the Nemi ships were recovered, most historians dated the invention of the ball bearing to the Renaissance, to Leonardo da Vinci's sketches in the 1490s. The Nemi discovery pushed that date back by over 1,500 years. Roman engineers working with bronze and wood had already solved a problem that the rest of the world would not revisit for a millennium and a half, and then they lost it. On the night of May 31st, 1944, during the chaos of the German retreat from Rome in World War II, both ships were destroyed by fire in the museum that had been built to house them. The bronze fittings, including some of the bearing components, survived because they had been removed for study. But the ships themselves, and much of the context that would have told us exactly how these bearings were designed and manufactured, burned. 2,000 years of survival on the bottom of a lake, followed by 12 years in a museum, ended in a single night of war. But the Nemi bearings were not the only example of ancient rolling mechanisms. Around 330 BC, more than 3 centuries before Caligula's ships, a Greek military engineer named Diades of Pella, who served under Alexander the Great, designed siege equipment that used linear roller bearings. His battering rams, mounted inside armored siege towers, called helepoleses, rode on lathe-turned wooden rollers that allowed the ram to slide back and forth with minimal friction. The rolling element was not contained in a race. It was not a modern bearing in any structural sense. But the principle, replace sliding with rolling, was being applied to military engineering 300 years before the Nemi ships demonstrated it could also support rotational loads. Now, here is something most people get wrong about technological progress. They assume it is linear. That once something is discovered, it stays discovered. That knowledge moves forward, always forward. The bearing proves otherwise. The Romans had ball bearings. The knowledge did not survive. When the Roman Empire fragmented and eventually collapsed, the institutional memory that preserved engineering knowledge, the workshops, the apprenticeship chains, the written records, much of it vanished. Medieval European engineers did not have access to Roman bearing designs. They started, in many ways, from scratch, and what they built were plain bearings. The massive post mills of the 12th and 13th centuries, the earliest European windmills, pivoted their entire wooden bodies on a single vertical post. The weight of the mill, the sails, the grinding mechanism, everything rested on a bearing at the top of that post, where a horizontal beam called the crown tree sat on a pintle, a pointed iron tip. The entire building rotated around that single point, so the miller could turn the sails into the wind. That pintle bearing took the full weight of a multi-ton structure and had to allow rotation while resisting lateral forces. It was made of iron. It was lubricated with tallow, and it wore out constantly, requiring regular replacement. Medieval millers were, in a very practical sense, tribologists, people whose livelihood depended on managing the friction at a single point of contact. But the person who actually drew what we would recognize as a modern ball bearing was not a millwright. He was an artist, a polymath, a man who drew helicopters and tanks and parachutes 500 years before any of them existed. Leonardo da Vinci. In the Codex Madrid I, a set of manuscripts rediscovered in the National Library of Spain in the 1960s, Leonardo sketched designs for ball bearings around 1490 to 1500. His drawings show balls arranged in a circular race supporting a rotating shaft. And he noticed something that would not be formally addressed by bearing engineers for another 4 centuries. When balls and a bearing touch each other, they move in opposite directions at the point of contact, creating friction between the balls themselves. Leonardo's solution was a cage, a separator that kept the balls evenly spaced and prevented them from rubbing against each other. He even noted that 3 balls under the spindle are better than 4 because 3 points of contact provide inherent stability while 4 might leave 1 ball unloaded. That is precision engineering intuition 500 years ago, recorded in the margins of a notebook. But Leonardo's designs were never built. His notebooks were private. They were not published. They sat in archives for centuries, unknown to the engineers who would eventually reinvent everything he had drawn. The bearing had to be discovered again and again and again. Think about what that pattern tells us about the bearing as an invention. It is not like the printing press or the steam engine, a single breakthrough that changed everything in a single moment. The bearing is a convergent invention. Multiple cultures, separated by centuries and continents, arrived at the same solution because the problem is universal. Anything that rotates needs support. Anything that supports rotation fights friction. And the physics says, roll, do not slide. The solution keeps being rediscovered because the problem never goes away. The next major step came from an unlikely source. Not an engineer, not a scientist, a clockmaker. In the 1730s, John Harrison, a self-taught English carpenter and clockmaker, was trying to solve the greatest navigational problem of his age, the longitude problem. To determine your east-west position at sea, you need an accurate clock, one that can keep time to within a few seconds per day despite the rocking of a ship, changes in temperature, and the corrosive salt air. The British government had offered a prize of £20,000, roughly several million pounds in today's money, to anyone who could solve it. Harrison built a series of marine timekeepers. His third clock, H3, introduced something the world had not seen before: a caged roller bearing. Small rollers contained within a cage, supporting the moving parts of the clock mechanism with minimal friction. It was not a ball bearing, it was a roller bearing. But the principle was the same as Leonardo's sketches, which Harrison had never seen, and the motivation was not transportation or manufacturing. It was time. Harrison needed to reduce friction in his clock to such a degree that the mechanism would keep accurate time for months at sea without maintenance. The bearing was his solution. Harrison's H3 never won the longitude prize. That honor went to his fourth clock, the H4, a pocket watch-sized marvel that took a different approach entirely. But the caged roller bearing he developed for H3 survived as an engineering concept. It was one of the first practical implementations of a contained rolling element bearing in a precision instrument, and then came the patent that changed everything. In 1794, a Welsh ironmaster named Philip Vaughan of Carmarthen was granted what is widely recognized as the first patent for a ball bearing. His design was straightforward: iron balls running inside a groove, a ball race between the axle and the wheel hub of a carriage. The balls rolled, the wheel turned, the friction dropped. Vaughan was not a theorist. He was an ironmaster, a man who worked with metal every day and understood from practical experience that a ball rolling inside a groove offered less resistance than a shaft grinding inside a hole. His patent is the formal beginning of the modern bearing industry. Every ball bearing manufactured today is a descendant of Philip Vaughan's 1794 design. But there is a gap between a patent and an industry. Vaughan's bearing worked, but it was handmade. The balls were not perfectly round. The races were not perfectly smooth. The materials were inconsistent. To make bearings at scale, you needed a way to produce perfectly spherical, perfectly hard steel balls by the thousands, and that problem was solved by a bicycle mechanic. In 1869, a Parisian mechanic named Jules Pierre Serre was awarded French patent number 86680 for a radial ball bearing designed for bicycles. The early velocipedes, the bone shakers, suffered from enormous friction in their wheel hubs. Serre's bearing reduced that friction dramatically. And the proof came just months later, in November 1869, when James Moore used a bicycle fitted with Serre's bearings to win the world's first major city-to-city road race, from Paris to Rouen. The bicycle, it turned out, was the perfect proving ground for the ball bearing, lightweight enough that even small improvements in friction made a noticeable difference, popular enough that demand for better bearings was enormous, and cheap enough that manufacturers had to figure out how to produce bearings not one at a time, but by the thousands. Think about that connection. The bicycle, a vehicle most people think of as simple, was the industrial crucible for the ball bearing. The mass market for bearings was not trains. It was not factories. It was bicycles. The demand created by millions of people wanting a smoother ride on a two-wheeled machine drove the engineering that would eventually put bearings inside everything from jet engines to hard drives, and the man who made mass production possible was Friedrich Fischer. In 1883, Fischer, a mechanical inventor in Schweinfurt, Germany, who ran a bicycle shop, built a machine that could grind hardened steel balls to near-perfect sphericity. Before Fischer's machine, steel balls were manufactured on turning machines in England, a slow, expensive process that produced inconsistent results. Fischer's ball grinding mill used a grinding wheel tilted at a precise angle, roughly 1.9 degrees, that forced the balls to rotate on multiple axes during the grinding process. The result was balls accurate to within 20 micrometers, 20 thousandths of a millimeter. For the first time in history, perfectly round, uniformly hard steel balls could be produced in bulk. Fischer's company eventually became FAG, Fischer's Aktiengesellschaft, one of the largest bearing manufacturers in the world, now part of the Schaeffler Group. And Schweinfurt, that small Bavarian city, became the ball bearing capital of the world. How important was Schweinfurt? Important enough to bomb. On August 17, 1943, the United States 8th Air Force launched a double-strike mission against Regensburg and Schweinfurt. The target at Schweinfurt, the ball bearing factories. Allied intelligence had identified Schweinfurt as the source of roughly 40 to 50% of Germany's ball bearing production. Without bearings, No engines. Without engines, no tanks, no planes, no submarines. Albert Speer, Hitler's armaments minister, later admitted that the raids caused him serious concern, noting that bearing production fell by roughly 34 to 38% after the August raid. But the mission was catastrophic for the attackers. 60 B-17 bombers were lost. The 8th Air Force went back on October 14, 1943, in what became known as Black Thursday. This time, 291 B-17s attacked Schweinfurt. 77 were shot down, a casualty rate exceeding 26%. The losses were so devastating that the United States temporarily suspended unescorted, deep penetration daylight bombing raids until the P-51 Mustang, with its long-range escort capability, could be deployed. But the raids ultimately failed to cripple German production. Speer ordered the dispersal of bearing manufacturing to smaller, harder-to-target facilities. Germany increased imports from neutral countries like Sweden and Switzerland. Stockpiles cushioned the blow. And the Allies did not follow up with sustained attacks frequently enough to prevent recovery. Still, think about what that campaign reveals about the bearing. In 1943, the Allied High Command looked at the entire German war machine, every weapon, every vehicle, every piece of industrial equipment, and concluded that the single most vulnerable choke point was the ball bearing. Not the steel mills, not the oil refineries, the ball bearing. A metal sphere the size of a marble was considered the Achilles heel of an industrial superpower. That is how central bearings had become to modern civilization in barely 50 years. Let's go back to the engineering, because in the late 19th century, 3 developments happened almost simultaneously that transformed the bearing from a useful device into the foundation of the modern mechanical world. The first was Henry Timken's tapered roller bearing. In 1898, Timken, a successful American carriage maker, was granted 2 patents for a bearing that used conical rollers instead of balls. The taper was the key. Standard ball bearings handle radial loads well, the weight pressing down from above, but they struggle with axial loads, the sideways forces that a wheel experiences when a vehicle turns. Timken's tapered rollers handled both simultaneously. The conical shape distributed both radial and thrust loads across the full length of each roller. Within 2 years, Timken was selling axle assemblies to early automobile manufacturers. By 1923, his company produced 90% of the bearings in the United States. The tapered roller bearing did not just improve carriages, it made the automobile practical for daily use. Without bearings that could handle the combined forces of weight and turning, car wheels would have failed on every corner. The second development came from Sweden. In 1906, a young operations engineer named Sven Winquist was working at the Gamlestadens Fabriker textile mill in Gothenburg. The factory had been built on soft, unstable soil, and the buildings had settled unevenly, causing the drive shafts that powered the machinery to fall out of alignment. The bearings of the time could not tolerate misalignment. When a shaft was even slightly crooked, the bearing overheated, seized, and failed. Winquist's solution was elegant. He designed a double-row self-aligning ball bearing with a spherical raceway in the outer ring. The inner ring could tilt freely within the outer ring, accommodating misalignment without losing function. In 1907, he was granted Swedish patent number 254006. That same year, he founded Svenska Kullerfabriken SKF. Today, SKF is one of the largest bearing companies on Earth, producing bearings for everything from wind turbines to surgical robots. An engineering problem at a textile mill on swampy ground in Sweden created a company that currently operates in roughly 130 countries. The third development was theoretical. In 1883, a British engineer named Beauchamp Tower was conducting experiments on lubricated journal bearings for the Institution of Mechanical Engineers when he made an accidental discovery. He drilled a hole in a bearing for lubrication and noticed that oil was rising up through the hole, even pushing out a wooden plug he had used to block it. The oil was under pressure. Inside the bearing, the rotating shaft was dragging oil into a converging wedge-shaped gap, building up enough pressure to separate the metal surfaces entirely. The bearing was not metal on metal, it was metal on oil on metal. The surfaces were floating. In 1886, Osborne Reynolds, a physicist at the University of Manchester, published a paper explaining exactly what Tower had observed. He derived what is now called the Reynolds equation, a mathematical description of how a thin film of viscous fluid generates pressure sufficient to support a load. This was hydrodynamic lubrication, the theoretical foundation for every fluid film bearing in existence. Every turbine shaft, every ship's propeller bearing, every crankshaft journal, and every internal combustion engine operates on the principle Reynolds described. The surfaces never touch. They ride on a film of oil a few micrometers thick, and the physics of that film is what keeps the machine alive. Reynolds turned Beauchamp Tower's accidental observation into a science, and that science made the Industrial Revolution's machines not just possible, but durable. Now, here's where bearings become something most people never think about but cannot live without, because bearings are everywhere. Not metaphorically, literally everywhere. A typical modern automobile contains somewhere between 100 and 150 bearings. Wheel hubs, transmission, engine crankshaft, water pump, alternator, air conditioning compressor, power steering, every component that rotates or oscillates requires a bearing. A commercial jet engine, a single engine, contains over 100 precision bearings operating at temperatures exceeding 300 degrees Celsius and rotational speeds above 15,000 revolutions per minute. A wind turbine, one of those enormous offshore installations generating renewable electricity, relies on massive slewing ring bearings, some over 4 meters in diameter, to control the pitch of the blades and the yaw of the nacelle. Those bearings must operate reliably for 20 to 25 years in salt spray, temperature extremes, and constant vibration, without maintenance. The global bearing market in 2026 is valued at roughly 156 to 159 billion US dollars. That number is projected to exceed 300 billion by the mid-2030s. Think about that for a moment. Bearings are a $156 billion industry. Most people cannot name a single bearing company. Most people have never thought about what is inside the wheels of their car. And yet, if every bearing on Earth stopped working simultaneously, every car, every train, every plane, every turbine, every motor, every pump, every fan, every washing machine, every hard drive, everything with a moving part would grind to a halt. Within seconds. Civilization does not run on electricity or oil or silicon, it runs on bearings. Everything else is just the thing the bearing makes possible. And bearings are still evolving because friction, the old enemy, has not surrendered. In the 1960s, engineers began developing magnetic bearings, systems that use electromagnetic fields to levitate a rotating shaft, suspending it in space without any physical contact at all. No balls, no rollers, no races, no lubricant, no wear. The shaft simply floats, held in position by active feedback loops that adjust the magnetic field thousands of times per second to keep the rotor centered. Active magnetic bearings are used in high-speed flywheel energy storage systems where a massive rotor spins at 20,000 to 50,000 revolutions per minute in a vacuum chamber, storing energy as kinetic motion. With no friction, the flywheel can spin for hours or days with minimal energy loss. Magnetic bearings are also used in turbomolecular vacuum pumps, in natural gas pipeline compressors, and in the maglev trains that levitate above their tracks at over 600 kilometers per hour, the entire train riding on a bearing that has no moving parts. And in space, where there is no air and no way to service equipment, bearing reliability is existential. NASA's Kepler Space Telescope, which discovered over 2,600 exoplanets, nearly lost its mission when reaction wheels, gyroscopic devices used to aim the telescope, experienced bearing failures. Investigations revealed that electrical arcing inside the reaction wheel housings was damaging the steel ball bearings. Engineers eventually mitigated the problem in later missions by switching to ceramic bearings, silicon nitride, which are electrically non-conductive and cannot arc. A single material change from steel to ceramic saved an entire scientific mission. The discovery of thousands of planets orbiting other stars depended, in part, on getting the bearings right. And here is one more detail that connects the very beginning of this story to the very end. Leonardo da Vinci, who sketched ball bearings in the 1490s, was also one of the first people to systematically study friction. His notebooks, unpublished during his lifetime, contain observations that Guillaume Amontons would rediscover 200 years later. Friction is proportional to load and independent of contact area. Leonardo was studying the enemy and designing the weapon at the same time. He just never got to fire it. So here's the answer. How did humans invent the bearing? They invented it in stages. First, they noticed that rolling reduces friction, probably tens of thousands of years ago when someone placed a log under a heavy object instead of dragging it. Then, around 3500 BC, Mesopotamian potters created the first true rotational bearings, pivot and socket systems that allowed a disc to spin on a fixed axis. Then, for 4,000 years, every wheel on every cart, chariot, and wagon used plain bearings, shaft and whole systems lubricated with animal fat. Around 40 AD, Roman engineers on Lake Nemi built the first known rolling element bearings, bronze ball bearings and roller bearings supporting rotating platforms on Caligula's ships. That knowledge was lost when Rome fell. Leonardo da Vinci reinvented the ball bearing in the 1490s, complete with a cage to separate the balls, but his designs stayed in his notebooks. John Harrison built caged roller bearings for his marine clocks in the 1730s. Philip Vaughan patented the first modern ball bearing in 1794. Jules Serre put ball bearings in bicycles in 1869. Friedrich Fischer invented the ball grinding machine in 1883, making mass production possible. Henry Timken patented the tapered roller bearing in 1898. Sven Wingquist invented the self-aligning ball bearing in 1907. Beauchamp Tower accidentally discovered hydrodynamic lubrication in 1883, and Osborne Reynolds explained it mathematically in 1886. And in the 20th and 21st centuries, bearings evolved from steel balls and steel races to ceramic hybrids, air bearings, and magnetic levitation systems where nothing touches at all. Was the bearing a single invention from a single source? No, absolutely not. The bearing is a convergent technology, reinvented independently across multiple civilizations because the problem it solves, reducing friction between moving surfaces, is universal. Mesopotamians, Romans, medieval Europeans, Renaissance Italians, Georgian Arab Britons, 19th century Germans, Swedes, and Americans all arrived at some version of the bearing independently. The physics demands it. Anything that rotates needs support. Anything supported while rotating generates friction. And friction destroys everything it touches given enough time. The probability that humans would discover some form of bearing, given the existence of wheels, axles, and the universal laws of friction, is effectively 100%. The concept is as inevitable as the wheel itself. But the specific form of the modern precision bearing, hardened steel balls and machined races with a retaining cage, that is a product of the Industrial Revolution, and specifically of the bicycle industry of the 1860s to 1880s. The probability that this particular form would emerge from this particular industry, rather than from clockmaking or railroad engineering or military applications, is lower, perhaps 40 to 50%. It was contingent on the specific market pressures and manufacturing challenges of the bicycle era. But some path to the precision bearing was inevitable. The probability that humans would develop a mass-produced precision rolling element bearing by the early 20th century through one route or another is roughly 95%. Tonight somewhere, a shaft is spinning inside a bearing. A wheel is turning. A turbine is generating power. A satellite is adjusting its aim. A surgeon's drill is cutting into bone. A child's bicycle wheel is coasting silently down a hill. Every one of these motions is possible because thousands of years ago, someone noticed that a round thing rolling between two surfaces made the world move easier. They did not call it a bearing. They did not know they were solving a problem that would define industrial civilization. They just knew that dragging was hard and rolling was easy. And from that single observation repeated independently across continents and centuries came the invisible infrastructure of the modern world. The bearing. The most important machine part you have never thought about.